Hi, folks. I'll share the presentation. Do you see the slides? Can you hear me? Awesome.
Yes and yes.
Yes and yes.
Yeah, you should very well visible.
2021 tech recap, past, present, and future of the Fluence development. It was a huge year for the Fluence team, so let's debrief. The structure will be like the following. I will say what we had in the beginning of the year, that what challenges we faced, what we did this year, what challenges we see right now, and what we want, what we plan to deliver next year. And I'll try to be short. So let's begin with archaic epoch. That's before 2021 or beginning the first days of 2021. So Fluence Network was already live for a few months. It launched in November 2020, but it was very basic. It had only the most necessary parts of it. So we had an Aqua virtual machine with an Aqua intermediate representation. So you were able to make distributed scripts in Fluence with this wonderful syntax with many brackets, which was kind of hard, but it was working. And its execution was synchronous on peers, but it also worked. We had Marine, our Rust, our WebAssembly runtime with basic tooling. It was working. And we had the Fluence node written in Rust as a reference implementation, and it was also working. But we had some challenges, we had some problems. The main problem was developer experience. So this low-level language doesn't really fit humans. It's made for the machines, so it's hard to use. We had no documentation, there was lack of tooling, so developer experience wasn't very good. Second, stability wasn't also like perfect, and we wanted Fluence Network and tooling just to work constantly with no critical issues. And we needed more core components to enable more fundamental use cases of the Fluence network, and to start develop Fluence on Fluence instead of developing Fluence itself. So that was the challenges. And now let's switch to the past, to the year. So we did a lot, and the story of the year is like a lot of things delivered, developed, and so on. I grouped them into some Aqua releases, Marine, peer implementations, built-ins, integrations, and documentation. So first of all, Aqua. Aqua is the language for distributed systems, and it's the main way to interact with the Fluence network. Over the year, we did a lot of upgrades into Aqua virtual machine. For example, we switched from synchronous to asynchronous Aqua virtual machine, which had a huge performance impact. We implemented CRDT streams, so data is really CRDT now that backs this Aqua VM execution. And we introduced a few new and very necessary Aqua VM instructions, AIR instructions. On top of Aqua VM, we have Aqua, and Aqua is around just since April. We developed the language, the compiler, and the basic, the fundamental tooling for the language on the first half of this year. And it changed like everything, because after that, we had this main way to interact with the Fluence network, and it's much more developer friendly. And to explain how to work with Aqua, we have an Aqua book now, so it's documented. You can read, you can learn, you can use it out of the box. For Marine, which is a WebAssembly runtime and tooling that we use, we delivered a lot of developer experience improvements. For example, now we have a Marine test extension, which allows you to test WebAssembly services as they are in WebAssembly. So you compile and you don't test your Rust code, but you test what actually will be launched in the browser or in the Fluence node. Then we implemented, but not yet delivered, not yet announced, Marine Web, the way to run Marine WebAssembly in browser and Node.js. This opens the doors to have the full-featured Fluence Peers implementation in JavaScript, which we'll do next year, hopefully. And there were we made a lot of more low-level improvements, like we introduced memory limits. So now memory is constrained for Marine, and resource consumption is better managed now. We provided pass by reference and more support for more basic Rust data types. Did some Rust SDK improvements, augmented the built WebAssembly with a self-describing WASM manifest, and like such things. Then a lot of things happened with Fluence Peers. The Fluence Peer actually is a combination of Aqua virtual machine, Marine as the way to run WebAssembly, libp2p for transport, and event loop to connect everything together. So first of all, this year, since this summer, we have Fluence.js with Aqua support. And actually, it serves as a Fluence Peer for JavaScript and TypeScript developers. It runs both in the browser and in Node.js. And also, what we developed but not yet announced, we implemented web workers for async Aqua VM pool, and it's quite performant. And it means that this Fluence.js Peer is quite full-featured, which is nice. Then the reference implementation of the Fluence node, Fluence Peer in Rust was rewritten to support asynchronous Aqua VM. We introduced the particle file vault. It's mechanics to transfer files between services inside one peer and inside one particle safely and securely. And it opens the gates for more integrations with external services. And we vastly improved the delivery of the Rust node. Now we support built-ins with the specific layout. We have some support for sidecars to have side processes, which can be used by the Fluence node, and like such things. Then this year, as I just said, we introduced the built-ins infrastructure. Built-ins are the parts of the core Fluence protocol delivered as WebAssembly services and intended to run both in the Fluence Rust node and the Fluence JavaScript peer implementation as well. We delivered Aqua DHT. Now it's named Registry. This is a resource routing solution. So in the distributed environment, you usually want to know what to call and where to call. And this is the most fundamental problem that you face when you begin working with Fluence on more high level. This is the basic solution, the fundamental solution for this problem. Then we developed and delivered, but not yet announced, the trust graph implementation. Is described in our RFC, and basically it's a decentralized public infrastructure, Fluence native one, that aims on managing priorities and permissions over the network. So it's now implemented, and we'll update documentation to describe it, and we'll have a dedicated community call beginning of the next year to describe it and to tell about it, because it's a big thing. Then we implemented IPFS integration, and it's quite important for us because like in general, it allows you to transmit and store files using IPFS network, and then manage them on the Fluence network, like do some computations, for example. But actually, we switched to IPFS as a default way to deliver WebAssembly modules over the Fluence network. So now you use IPFS to distribute services and Fluence to run them, to run computations. And you can run these computations on the IPFS stored data, which is kind of powerful. And also, not very built-ins, but we have provided out of the box some modules like curl, SQLite, and more, which are just basic building blocks to make your services if you want some. Then this year, we made a few integrations with other protocols, like implement some bridges or adapters and deliver them as services. As I mentioned, we have IPFS, but we also have ceramic, near, and Ethereum integrations. So if you want to use, if you want to have some interoperability with these networks, you can at least begin with these adapters and provide pull requests with improvements if you miss something, but you don't need to start from scratch. And this is about unlocking more use cases, fundamental use cases of the Fluence network. So now it's much faster to get something useful with what we have. And finally, with all of this, to support all of this and to deliver it to the community, we have documentation. We have the main Fluence docs on the fluence.dev website. We have Aqua book on fluence.dev/Aqua book. And we have we maintain the repository with examples and tutorials for every part of Fluence. So you can learn how to use Aqua, how to use Marine, how to make services, how to connect services, how to connect peers, and all of that. And we kind of support these examples repo, so they are up to date. And it's the best way to learn how to build things with Fluence. So all of that we delivered this year. And now, what's the situation right now? First of all, over the year, the Fluence network matured a lot because it's 1 year older. And now we have more complete tool set for Marine and Aqua. So all the tool set just works out of the box. It's tested, it's like used by main developers. It works, it's documented. We have examples, we have services, we have integrations. You can learn how to make services or how to make integrations by reading the code that already exists. And the network is stable enough. So we have over the last months, we usually have one or many hackathons going on at the same moment, and it has no significant impact on our nodes that we provide for the Fluence network, which is kind of nice. But it could be even better. So we have some domains, some parts of Fluence to improve. First of all, Aqua is currently too simplistic. We want more language features to develop complex algorithms. We don't have too many sources in Marine, but the main feature of the Fluence network is reusability and composability with Aqua, and you need to have more things provided by the network to compose. And currently, to develop a service and to provide it to the network, the only way to do it is to develop in Rust, but it creates an entry barrier. So we want to have more JavaScript or TypeScript or Aqua experience enabled for the service development. So basically, we want to have more primitives so that there is no need to develop these primitives to have product. So the goals basically is to provide a low-code solution, to provide more reusable parts like algorithms, services, data accessors, adapters, bridges, and so on. Second, security system is not feature complete currently. We need to provide some cryptography and resource consumption management and such stuff. And finally, we want to enable the community to make scalable Web3 native components and like protocols. And to do so, we need to enable more complex algorithms, distributed algorithms. So now let's switch to the future. As Aqua is the main entry point, then the first part of the future is the roadmap towards Aqua 1.0. To enable Aqua 1.0, first we need to advance Aqua virtual machine. And there is a huge list of fundamental capabilities that we are missing now and that are in development currently, like recursive streams, functors, cofunctors, garbage collection, binary error representation, stream cannibalization, and some more. You can take a look on the Aqua VM repository if you're curious. And these features unlock different features of the high-level language of Aqua, like abilities, the modularization, and internal composability approach of Aqua, lambda expressions or handling patterns, and more primitives. And the goal for these language primitives, for this syntax and semantic, is to provide algorithms and libraries which are to be delivered in Aqua. It's a more complex, more feature-rich trust graph and registry, but also we need to switch to the Fluence Demlia, which should be written in Aqua and Marine, and it will enable, finally, development of protocols. So the goal is to commoditize the development of distributed protocols by the Fluence community to make it as the new domain in the Fluence tool set, to provide tooling, to make it simple, to make it stable, scalable, and so on. So this will be one of the main topics for the next year. And for overall Fluence development schedule, it's a lot of core protocol features, developer experience, and we want to have more and more connections to the community. We want to react on the community needs. So speaking about the protocol and like the core features, first of all is security. We want to have more signatures in particles and registry. And currently, you can run the Fluence node, but it's hard to secure it and to set up permissions on different resources to manage resource consumption on the node. So this should also be sorted out next year. Then to develop and to secure protocols on Fluence, we need to describe distributed invariants in Aqua, which enable and constrain composability at the same time. And to protect from amplification attack, we want to introduce distributed guess, which is a part of Aqua VM actually, but it relates to security. Then we have many performance updates, garbage collection, foreign function interface improvements, data formats, serialization, deserialization. There's a lot of things which are made not absolutely optimal and can be done better. That's about the core. And about developer experience and the community, first of all, we want to have more integrations, more and better deeper integrations with other protocols. And one of the goals is to provide DAO protocols and to enable faster go-to-market for the community, for the projects on top of the Fluence network. We want to have a full-featured JavaScript peer with with ability to develop services fast in JavaScript or TypeScript, and if you need to scale it, rewrite it to Rust later and move it to WebAssembly later, but experiment in JavaScript. And we plan many improvements for developer experience and for user experience as well, because we want to deliver different front-end applications for different use cases and target audiences of the Fluence protocol. And overall, we will be speaking more with the community, and we are ready to hear back because we want to provide more value to the community and to have more community involvement. So that's beneficial to all. And that's all. That was a quick tech recap of 2021 from me, Dmitry, and from the Fluence team. See you in the new year, 2022. Hope it will be even huger. Thank you.
I'm sure it will be, Dmitry. Thank you very much. Evgeny, do you want to add?
Well, no, I'm good. I think it was great, great update from Dmitry covering pretty much everything.
Okay. Anna, I know I'm springing it cold on you, but if you want to add something, maybe really brief about the hackathons and events we had this year, just real brief.
Well, we had about eight hackathons this year. Participate. Sorry, somebody had. Okay. Yeah, and met a lot of hackers through the hackathons and events. We had also offline events during Lisbon Blockchain Week and in Helsinki during Slush. And it was amazing to see people really engaged in the topic and, interested about Web3, about Fluence as such. Sorry. For the next year, the plan is to participate in more hackathons, to post the bounties, to engage people more in in the Fluence stack and building projects with Fluence. The nearest hackathons we are going to have is Denver in February. If anybody's going there offline, let's meet offline. There are going to be a week of events. If you are not going to be there, they will have also online version is 1 week of hacking. We will be posting all the news about that. And also we are planning to do a hackathon, in-person hackathon in Moscow during the next year. And more news to come. We will post everything in our channels. And I want to thank everyone who've been with us during this year. It was amazing. And yeah, let's keep it going. Thank you.
Cool. Yeah, it was great. Great with those hackathons. It was a lot of fun. And I think we got some really quality submissions. It was awesome. And questions? Anybody have any questions before we get to Alexey's overview of the Rust node? Well, without further ado, Alexey, take it away.
Yeah, thanks. Hello, everyone. It was a really enormous year. So let me share the screen. Do you see everything? I'm not sure.
Yes.
Yeah, do you see diagram and the code?
Yes,
Yep.
zoom it a little.
Yes, we do.
Okay, if I need to make it like zoom in to you, just tell me. So on the right is a sequence diagram of how Fluence Peer works on the high level, Fluence Rust peer. It's mostly the same for the Fluence peer because they're solving the same tasks, so they're structurally alike. So let's take a look at what's going on. Here, the structure is as follows. So on the left, these other peers, it's just the whole network, and all other peers, all the networking is there, all the network, and all the elements on the right, those ones, that's the structure of a single peer. So all the lines except the first one is about a single peer. We're looking inside of a peer. So what peers in Fluence network do most of the time? They exchange particles. So when a user sends some, when a user wants to execute something on Fluence network, she writes Aqua script, compiles it, and sends to the network. And that to send to the network, it means to connect to some peer and send particle. So that's the first steps that we see here. Some peer connects to us. We receive that connection, even connect back, and then we receive a particle. Particle contains inside, particle contains data, script, and time to life. Script is what dictates what should happen, like it's the executable code. Data is all the data that accumulated while the script was executed. Like this script could come to us after being executed on tens or hundreds of other peers, and all they put some variables, some call results, some routing results. All this goes to data. That makes particle stateful. And time to life, it says how many milliseconds should a particle live after it was sent. For example, I can say, here is a particle, send it to the network and say this particle should be executed for 60 seconds or less. Like if it somehow looped or something happened and it executes more than 60 seconds, then all peers will just drop it. Okay, so we received a particle. Usually our peer receives a lot of particles and it should maintain some performance levels, some latency. Some latency should be manageable so users can receive their response timely and their UI works smoothly. So for that, we use a few queues. Basically, what Fluence Peers is, it's a queue and a big loop. You can see it's a big one here. So we have a particle queue. It's called, it's inside an entity that's called dispatcher. It dispatches particle execution and all that follows. It has a single queue, and it has a particle queue and a big loop that dequeues from that queue and executes particles concurrently. So it has some threads, some parallel and concurrent execution, and all particles, they execute at the same time until the thread pool is saturated. So it's like 16 particles at the same time if you have 8 cores or something like that. So when dispatcher sees a new particle in the queue, it takes it and sends to execution to Aquamarine pool. What is Aquamarine? It's a layer of execution for particles. So it takes a single particle, finds some executor for it, and executes, interprets the script, applies the data to that script, and gives some results back. What kind of results come out of particle execution? 2 kinds of results. First one is where to send particle next. And second one is what to do with that particle, like call some code or do nothing, just forward it to some other peer in the network. So to execute a particle in a way that still maintains good performance on the node, we need to have several executors. Each particle executor is called Aqua VM. That's basically an interpreter in WebAssembly and the WebAssembly runtime together. They receive particle, execute its script, and return results back. We have a whole pool of such executors. Like on every node, there is 8 or 16, depending on number of cores, of such executors. That means that we can simultaneously execute 8 or 16 particles. That also means that those executors are sometimes busy or are sometimes free. And when particle comes, we take it from the queue, try to acquire a free executor, and then execute the particle. Now, in order, all particles have ID, like all particle has particle IDs. It should be like here as a fourth field. That means that the same particle can go to the same peer several times. Like I receive this particle, send it to other peer, it sends it back, and that could happen like simultaneously. A lot of the same copies of the same particle could arrive at me if we were talking about parallel execution. And that poses a problem. If we are to execute particle with the same ID concurrently, then we will have data race. We will race on the field, on this data field in the top left corner. And in order to avoid that, we introduce actors. Actor is created per particle ID. So if we receive a lot of particles with the same ID, they all go to the same actor. The actor has a queue inside it, and we enqueue particle into the actor. That gives us serializability. That means that all particles with the same ID on a single peer, they are executed sequentially as they arrive. First in, first out. So, yeah, first in. Anyway, so what we see here, when actor receives a particle, it asks the executor pool for a free executor, for a free Aqua VM. If there is a free Aqua VM, it's allocated for that actor, and actor can begin the execution. It submits script and data to the executor, to the Aqua VM. Aqua interprets error script and returns result back. As I said, there are two kinds of results. It's either next peers to forward particle to, or service calls. That's basically some code execution. So every particle, it could be either routed further to the network or trigger some code execution locally, or both. That's how particles, that's two effects of particles. First one is network effect, send me somewhere. And second one is code execution effect, like do something right here. Now, for each of the service calls, we execute them concurrently on the same node, basically in the same actor. We execute all the service calls in parallel if we have 3 threads that can take this work. So, for example, it could be at the same time, it could be some operation like SQL write to one database, and at the same time read from registry some value. And those two operations, they can happen at the same time. They don't depend on each other, so they can be paralleled, and that's what happens. That allows for higher throughput of code execution. That means that even if script contains a lot of operations on the same peer, they will all execute at the same time. That's a pretty novel thing to have in our peer, because previously it was all synchronous, like several months ago it was all synchronous. So, and it caused some performance troubles, like queue wasn't dequeued fast enough, and particles were all struggling in that queue and timeouts happening. Now it doesn't happen because we process the particles asynchronously and we don't clog the queues. Okay, so particle gave us some service calls to execute, and we executed them concurrently. It also gave us some next peers to forward particle to. For all, if we have some peers to forward particle to, we just do that. We forward, our actor forwards particle back to the dispatcher. Dispatcher forwards it back to the network layer, to the connection pool, and connection pool finally forwards it to other peers. This situation actually is a little bit more complex, because when dispatcher receives a network effect, like a forward particle somewhere, it has to find that peer. Yeah, so we have like a network effect that's a particle and the list of peer IDs. And those peer IDs, they might not be yet connected to our peer. So we have to find them. For that, we use Kademlia. It's not visible on this diagram because it would be too much. It's already too much. But that's what happens. We before we send particle to connection pool, we first discover the peer through Kademlia, connect to it if it's available, and only then we send particle to connection pool that's already connected to the peer we want to be connected to. Okay, so what else I found really interesting about this, the particle execution, is this piece, or the 14th step that I haven't described yet. So when we execute service calls, some code that particle has asked us to, we need to re-enqueue particle back to the actor. Yeah, so like that's because when we execute some code, we go through the script, like we execute one line in the script, it asks us to write something to database, then it executes the next line that asks us to read something from database. And we can't execute the second line before we execute the first line, because they depend on each other. And that means that when we execute write into database, we have to re-enqueue particle to be executed further, to go further through the script. And that means that when we execute some code, we get result back, and we write that result to the data, almost like that, to the data, and we submit the particle back to the executor. And this way we progress through the script line by line or by several lines if they are marked as parallel and can be executed concurrently. What that means is that we have here a loop that can go on almost forever until TTL expires. Because when we go further through the script, when we progress through the script code, it's possible that we receive more service calls and more next peers. So every iteration of the particle execution could yield more next peers and say, send this particles further to the network and execute more code. And that's a process that can go for a long time if a user asked network to do that. And that's pretty interesting process. I find it pretty interesting because yeah, it allows for very fast and very asynchronous execution of code. And it's great that we have it now. So that's basically the whole diagram we have here. How much time I have? Well, let's try to take a look at the code that implements this diagram. So as you may know, Fluence Peers, they use libp2p to communicate. In case of Rust Fluence Peer, we use Rust libp2p. Rust libp2p defines it has a very interesting architecture. It's kind of like actors and delegates at the same time. So what we have here, if we have network behavior trait. If you're familiar with Rust, it's just like if you're not familiar with Rust, it's almost like an interface. So this interface defines a few methods that we implement. First of all, we implement inject connected. That means that that's a method that's called when someone connects to us. It's the first step here in the diagram. We receive connection from that peer ID. We like write it down, and we now remember that we're connected to that peer. The second point on the diagram is receiving of particles. Here, that's a method. For that, we have a method that's called inject event. When it's called, that means that from this peer ID, we received the following event. The event is usually particle. It could be some errors or something else, but most of the time it's a particle. So what we do, we put particle to the queue, and we ask thread pool to wake up and send and trigger us because each connection pool on a node, it's like a stream. If you're familiar with Rust, then it basically implements a stream interface. And that's why I find Rust libp2p architecture pretty interesting, because every thing that does something, it works almost like a stream. So when we asked, after we asked thread pool to wake us, it calls method poll that basically asks stream to give more elements if they're available. What we do here is we look at our queue that we just enqueued the particle. It's a local queue. And if we have a particle there, we send it to the dispatcher. That's exactly what happens here. We have connection, what's described here, we have connection pool, and we send a particle to dispatcher. It's a usual Rust channel, like in Go, they have channels, and in Rust, we have channels too. Almost everywhere, in every programming language, we have something like this. Now, when dispatcher receives a new particle in the particle stream, in the particle queue, it takes it concurrently. If there are a lot of particles, they will be executed at the same time, and it sends them to Aquamarine pool, to the Aquamarine layer. Now let's take a look at the Aquamarine layer. What we have here. Here we also have a queue. It's called inlet, meaning that it's like a receiving port. It's a queue basically, and we take particle from that queue and we ingest it, meaning that we now are creating the actor. If it didn't exist yet, we either find it or create if it's not existent. And we say, hey actor, please ingest this particle. And actor ingests the particle. Where is the ingest method? Here it is. And it puts the particle to the mailbox. So you see we have everything in queue. Like we have a lot of queue, like a queue for each layer. We have a queue for each layer. Okay, and this actor, it acts also as a stream, meaning that it has a poll method that's called by the thread pool, asking actor to progress in the particle execution. And what we do here, we take from our mailbox, we take particle, like we have a method poll next that asks actor to take next particle if it has done executing the previous one. So if actor is still executing, we just exit and deallocate, and return Aqua VM back to the pool. Because for every call to the actor, Aqua VM pool is allocated from the Aqua VM pool. Hopefully it makes sense still. Like we have a pool of executors and we have to allocate executor if there is a free executor, like we have 16 executors and all of them could be busy, or all of them except one could be busy, and we take this one and send that executor to the actor so it can use it. But if actor is already busy, it just returns it back, says I can't execute more particles right now, because we need in actor we need to guarantee sequential execution. Okay, so if an actor is ready to execute particle, it executes it. It sends it to the Aqua VM, as said on the diagram. Aqua VM executes it asynchronously, and this execution yields a feature. It's like a JavaScript promise, Scala feature. It's a notion of asynchronous computation, and is executing works by checking that future is set. The future is set, the promise. So we have two poll methods in actor. First one I already described. It asks actor to take next particle, and the second one asks actor to return results back if it already executed the particle. So it just pokes future. It says, hey future, are you already finished? And if you're finished, please give me back network effects, and I will roll the particle further through the network. All the service call execution is encapsulated inside actor. It happens here. If particle yielded only service calls but didn't yield any next peers, it will keep executing until it either yields nothing at all, then it will stop execution, or until it returns network effects. In that case, it will route the particle further in the network. Yep. What happens if particle asks to execute service call? Then we go to the built-ins. What's the built-ins? Built-ins is this big switch case, big pattern matching thing that defines all the built-in API of the node, like in Fluence, you call service by service ID and by function name. Like you say, for example, you say SRV list, meaning that you want to see all the services running on the node, on the peer right now. Or you can ask the peer to do nothing. In that case, you just say op node, and it will just do nothing. Sometimes it's useful. And things like that. That's the whole API of the built-ins that we have on the node, on the Rust peer. It's almost the same on the Fluence.js peers, except that Fluence.js doesn't have Kademlia, and it doesn't have the SRV and dist namespaces, because until we have Marine Web on the Fluence.js, we can't create new services from WebAssembly. So those two blocks, they are dedicated to creating WebAssembly services. Okay, and in case none of the built-ins matched to the service ID function name, we go and check for the created WebAssembly services. They created WebAssembly services have their IDs in the form of UUIDs, universally unique identifiers. So it's basically a long string with alphanumeric and dashes and a function name. And it's a very simple thing. We have these services. It's basically just a hash map of all the services. It's like a little bit complex. So it's a hash map from string to service. It's wrapped in locks because it has to be, it has to provide concurrent access, but that's basically a hash map. So let me go back a few steps. So if we didn't match our service ID and function name against the built-in API, we just go and look into the map of UUIDs in the WASM services that Node has running at the moment. And yep, and the last thing, this yellow block here. Once actor returns network effects, they, through the magic of channels, of Rust async channels, they go back to the dispatcher and like to this, to the effects stream. You see, it's just a stream where each item is effect, which is always a network effect, which is, as said here, just a particle with a list of peer IDs. Okay, so for each effect, what we do is we execute it. Very simple. We do it concurrently, and executing an effect means that what we do here, we resolve the target peer ID through Kademlia, and once we resolved it, we ask connection pool to send the particle to resolved peer ID. Resolved peer ID means that from peer ID, we receive back peer ID and multi-address like IP4, some IP address, port, things like that. So we basically look for the network address on the Kademlia and connect to the peer, and then we can send particle. And that's it. That's how the Fluence Rust peer works. For the Fluence.js peer, it's almost the same. In case of Aqua VM executors, we have web workers now. Hopefully, we will have a pool of web workers very, very soon. And everything else is the same for Fluence.js peer, except that it's single-threaded in all places except the Aqua VM executors, which are, as I said, backed by web workers. So that's it from me.
Great, Alexey, that was awesome. Thank you. Questions, everybody? Anybody? No? Oh. Well, then I have one, Alexey. And basically, in Dmitry's presentation, he mentioned that curl, for example, were available but not built-ins. So for our developers, how would you explain the difference, and how is availability of these other services guaranteed?
So the availability is guaranteed. So the difference. We have built-in services like IPFS, and they look like this. The description of those built-in services, it looks like this. So we have free, so let me open. It's a pretty, it's a nuanced question, because you see we have built-ins here and they are really hard coded into the node, like node hard codes the name of functions and things like that. Also, we have WebAssembly services that can be deployed on demand. And also, we can name those WebAssembly services and give them human readable names. For example, we can deploy some WebAssembly service and it will have ID of UUID, long alphanumeric ID. And then we can say, hey, please add alias for this service ID. And if someone writes Aqua IPFS, know that Aqua IPFS corresponds to this big alphanumeric ID. And it's called service aliases. And every node, every Fluence Rust node is capable of starting WebAssembly services, of deploying them on node start. So when node starts, it downloads service package from this URL and deploys it and assigns this alias to it. And that makes a service a built-in in a sense that when you run a node, it's deployed immediately or just restarted if you restart the node. And it's always available. You can always go and use Aqua IPFS, Aqua DHT, that will be called a registry soon, and Trust Graph. They are built in. So regarding the curl, it's a little bit different story because they are available on the GitHub. You can download their WebAssembly files from URL and deploy through this API. You can create a service that uses curl WebAssembly inside that links against it and uses curl function in your service. And it's always available because you can always download it from GitHub, upload to IPFS, and deploy on the Fluence node. So that's what Dmitry meant, I suppose. Did I answer your question?
What I actually meant was, so this is great. So we got these pre-built WebAssembly modules, right, ready for deployment. But the actual resource is not provided by the node. The actual resource is provided by the underlying operating system, right? So the curl service is provided by a layer below.
Well, yeah.
The binary.
Yeah, when you have a WebAssembly module, you have service, and services consist of WebAssembly modules, and each WebAssembly module is able to call binaries that are available on the operating system's file system. Like you can call curl, or you can call echo, you can call IPFS binary, you can call whatever you want if you write WebAssembly wrapper around it. So in case of Aqua IPFS, it is backed by binary that's available on the file system, the IPFS client, written in Go and compiled to Linux binary. And WebAssembly Aqua IPFS service, it calls that binary to access the IPFS daemon that's also running next to the Fluence node. Yep.
Very good. That's exactly what I wanted to hear. Anybody else have any questions? Well, on that note, we'll wrap up. Thank you, everybody. It's been a great year. Thanks for sticking around. Hope you get a lot out of it. And we're looking forward to seeing you all in 2022. Happy holidays. Happy New Year. And see you in, what, Anna, 2 weeks? 3 weeks.
3 or 4.
There you go.
announce it.
All right.
And
Hey,
I
thanks everybody. Have a great day.
Yeah, and I guess in between we all in contact in Telegram. If you are not in Telegram groups, our groups, please join. Yeah, so we always connected, and the next call gonna be in January, I guess.
Happy
Right.
holidays.
Thank you, everyone. Oh, can anyone post the Telegram group link? Maybe I.
Sure.
Hey JP, this is the link, and we have also developer updates that we are usually shooting there. Yeah, this is we have many actually, many groups, many different groups. Anyway, so
We also have Discord.
yeah, and the Discord. All right. Yeah, and this Fluence.chat is a link that leads to always valid invitation to Discord.
Yeah, and all of those links are mentioned on in our documentation, fluence.dev.
So if you start digging in, you will find all these things anyway.
Bye-bye.
All right.
Bye-bye.
Thank you,
Thank you,
guys.
Alexey.